Well, good morning and happy Monday. So what I am planning on doing today is we will look at an ion exchange example where you have been asked to design a fixed bed ion exchange column. You're softening water and the flow rate is 0.876 cubic meters per second. That's equivalent to 20 mgd. The temperature of the water is 10 degrees C. You're told that the raw water has a total hardness of 40 milligrams per liter calcium carbonate, and you wish to soften that to 100 milligrams per liter as calcium carbonate. So let me ask this question. Why don't we just want to soften the water down to essentially zero hardness?
Doesn't it make it less resistant to pH changes?
One, if you consume alkalinity, it will be less resistant to pH changes, and
it becomes more corrosive.
So we want to make sure that we do have a passivation layer. We want to minimize the corrosivity of the water. So we don't want to soften to zero hardness. You're told that the maximum column diameter is to be 3 meters, and you should use a dualite C20 resin. We'll use sodium chloride to regenerate the exhausted resin, and the resin is available in sodium form, so we can purchase it in sodium form. Now, when you look up the material on the dualite C20 resin, you find that the softening capacity, when you're using 160 kilograms per cubic meter of salt as the regenerant, is between 1.35 to 1.55 equivalents. So this equivalence of hardness that we're removing per liter of resin. Leakage is 1%. So that means that even after regeneration, when we restart the column, we can expect to have 1%, or in this case, 4 milligrams per liter as calcium carbonate in our effluent. The maximum diameter should be 3. The bed depth can be between 0.75 to 1 meter. And the backwashing expansion should be 50% or more, and the backwashing flow rate will vary with temperature. The manufacturer also provides information about your service flow rates, your backwashing, regeneration, and rinsing. And we'll go through all of this information as we work through the problem. And also provides a plot for the bed expansion as a function of temperature and provides your flow rates. So let's start with this. Since we're given our exchange capacity in equivalents, let's convert the hardness to equivalents. So we have 400 milligrams per liter as calcium carbonate. We want the concentration in milliequivalents per liter. So how do we do that? It's Monday, it's early. 50 milligrams per milliequivalent. Where does that come from?
That's the equivalent weight of calcium carbonate.
Exactly. So we'll divide by the equivalent weight of calcium carbonate, and that gives us 8 milliequivalents per liter. Our desired hardness, so this is what we're looking for, was 100 milliequivalents calcium carbonate. So that's 2 milliequivalents per liter. So we also need to calculate the hardness in the effluent from the ion exchange column due to leakage. So I'll call it the concentration leakage is equal to that 8 milliequivalents per liter times 0.01. So that is 0.08 milliequivalents per liter. The next thing we need to do is to compute the
Professor, could you go back for a second?
Sure.
Thank you.
So the next thing we'll need to do is to compute the bypass flow rate to achieve the desired hardness level. So we have 8 milliequivalents per liter. That's what's entering in entering the column. So this is our ion exchange column. What's leaving the column is what? What's the concentration leaving the column?
2 milliequivalents per liter.
That's what we desire. So what's leaving the column? It's our leakage. But what we want is that 2 milliequivalents per liter. So what are we going to do to achieve a desired concentration of 2 milliequivalents per liter? What can we do? What's entering is 8. What's leaving the column is the leakage. What we desire is 2.
Could we bypass some of it?
Okay. We can't increase the concentration because think of that, that's what's coming from the wells. So we don't have much say in that, okay? So, but we can bypass. So what we're going to do is we're going to bypass some of the flow so that what we end up with is a desired concentration of 2 milliequivalents per liter. So this, we have Q bypass, we have Q treat, and we have Q, and I'll call this total. That equals Q treat plus Q bypass, and that equals the original flow rate, which is 0.876 meters cubed per second. So what we need to do is we need to develop a mass balance around that mixing. So we have Q treat times C leakage plus Q bypass times C, call it C bypass, which is that initial concentration. And that equals Q total times C desired. We've made some assumptions here. What are the assumptions we've made? Think back to the very beginning of the course.
Perfect mixing.
Okay, so perfect mixing. So that we have a CSTR around this complete mixing. What else have we assumed? The fact that I've written the reaction. Okay, exactly, steady state. And one more assumption. So we have no reaction. These assumptions are all for our mass balance around the mixing. And we also have, as I've written here, we have C total equals C treat plus Q bypass. We can also write that Q bypass is equal to some fraction of Q total, which means that Q treat is equal to 1 minus that fraction times Q total. And that allows us to do a substitution and then solve for the fraction. So if we substitute into the previous equation, to this equation right here, F is equal to 0.242. So we're going to bypass about 24%, about a quarter of our flow rate. And that should make sense. We started at 8 milliequivalents per liter. We want 2, that's a quarter, so we'll bypass. And because of the leakage, we bypass a little bit less. Does that make sense? I haven't substituted it in all the numbers, but I've given you all the values. So the bypass flow rate is 0.242 times the total flow rate, and that is 0.212 meters cubed per second. And the treated flow rate is 1 minus 0.242 times my total flow rate, and that equals 0.664 meters cubed per second. So this is what I'm treating through the column. This is what I'm bypassing around the column. So if we go back here, this Q here is 0.212 meters cubed per second, and Q treat is 0.664 meters cubed per second. So this is what we will continue to use as we move through the problem. Okay, so the total hardness that we're removing is this initial minus value from the leakage times my flow rate times 86,400 seconds per day times 1,000 liters per meter cubed, and that is equal to 4.54 times 10 to the 8 milliequivalents, and this is milliequivalents of hardness, that I'm removing per day. So that's what I need to remove. For the resin capacity, we'll pick the midpoint, and that was 1.45 equivalents per liter. So it was 1.35 to 1.55. We'll just pick the midpoint there. And the manufacturer also recommends that you reduce that value by 20% to account for non-ideality. So imperfect removal. So that would make an operating capacity. If you remember, we had talked about theoretical or total capacity and the operating capacity. And the operating capacity is what you actually achieve. The next thing we need to do is we'll pick a bed depth, and the bed depth needed to be at least 0.75 meters, could be less than 1 meter. We'll pick 0.9. The surface flow rate we'll get from that table that you were given, and that stated that the surface flow rate should be between 16 to 40 bed volumes per hour. We'll pick midpoint, so that would be 24 bed volumes per hour. And that means that it's 24 meters cubed of water per meter cubed of resin per hour. Okay, so that's what we mean by a bed volume. So we're treating 24 meters cubed per hour of water per meter cubed of resin. We stated in the original problem that we would use a 3-meter diameter. So the cross-sectional area of a column is pi d squared over 4, which is pi 3 squared over 4, which is 7.07 meters squared. So that's the cross-sectional area. We'll use a 3-meter diameter that was given. So the volume is just the area times the depth. So that is 7.07 meters squared times the 3 meter depth. I'm sorry, times the 0.9 meters depth. Sorry, that's what we said we were using. And that is equal to 6.36 meters cubed. So that's the volume per column. Any questions here? The total volume is equal to the total flow rate divided by the loading rate. So our flow rate is 0.664 cubic meters per second. There's 3,600 seconds per hour. And then we'll divide that by 24 meters cubed per hour per meter cubed. So this is resin, this is water. And that equals 99.6 meters cubed. So now we need to determine the number of columns required. So if we have 99.6 meters cubed, I'm losing my voice today, 6.36 meters cubed per column is the volume that we calculated. So we need 15.65 columns. So what do we do?
Round up.
Round up. Okay, so we'll round up to 16 columns. So the exchange capacity of each column is 1.16 equivalents per liter times 6.36 meters cubed times 1,000 liters per meter cubed. And that equals 7,380 equivalents. So that's the capacity in each column. And that equals 7.38 times 10 to the 6 milliequivalents. Since everything else was milliequivalents, just converted that, multiplied by 1,000 to get milliequivalents. So the service time of column operation is equal to your column capacity times the number of columns times the total hardness to be removed per day. So that's 7.38 times 10 to the 6 milliequivalents. That's per column. We have 16 columns, and we'll divide that by the 4.54 times 10 to the 8 milliequivalents per day that we need to remove. So just think about this, okay? For a 20 MGD plant, with columns this size, we would need 16 columns, and we need to regenerate every 6 hours or so. It's about 4 times a day. It's one of the reasons why we rarely use ion exchange when we have a high flow rate. 1 MGD, 2 MGD, reasonable number of columns. But you're talking here 20 MGD, 16 columns, and having to regenerate 4 times a day. Any questions? Okay, the manufacturer also stated, notice we're using a lot of manufacturing data, and that is the case with these ion exchange resins. Okay, so the manufacturer states that the total weight of salt required per column is based on 160 kilograms of salt per meter cubed of column. Each column is 6.36 cubic meters. So each time we regenerate, we need 1,118 kilograms of salt. The total weight of the salt solution, we'll assume a 10% salt solution, about 10,000 kilograms of salt. The volume of salt that we need is 10,000 kilograms. Specific weight, specific gravity of a 10% salt solution is 1.07. So each column, when we regenerate it, is going to need about 9.5 cubic meters of salt solution. The regeneration time is based on the information that we're provided here. And we're told that the rate is between 1.6 to 8 bed volumes per hour, and that the time needs to be between 30 minutes to 60 minutes. So between 0.5 to 1 hour. So let's pick, we need to start. So let's start by picking 4 bed volumes per hour. So we have 9.51 cubic meters divided by 4, that's meters cubed of water per meters cubed of resin per hour, times 6.36 cubic meters, and that is 0.37 hours. Is that sufficient?
No.
No. So what do we do? Because we said it had to be at least 0.5 hours.
Reduce the bed volumes per hour.
Exactly. So we'll reduce our flow rate. If we use 3 meters cubed per meter cubed, or 3 bed volumes per hour, and that is equal to 0.5. So we reduce the flow rate, and now we have 0.5. So that's sufficient. Questions about that? The next thing we need to do is to determine the backwashing flow rate. Notice we need at least 50% expansion, and we'll use this line right here. To be on the safe side, let's pick 60%. So we read across and then down, and that will give us a backwash flow rate of about 12 meters per hour. So that gives us the backwashing flow rate. We need a rinse rate. The table said it should be between 8 and 40 bed volumes per hour, and between 10 and 40 minutes. We'll pick the midpoint. So 24 bed volumes per hour and 25 minutes. And we can adjust that later, but this gives us a place to start. So the total service time is the 6.24 hours plus my 0.5 for regeneration, plus we'll do 25 minutes, and that was for rinse, and we'll use 10 minutes for backwashing. And that was again based on the data here. So the backwashing said between 5 to 15. So let's just pick the midpoint. So we'll use 10 minutes for backwashing. So this total service time, including regeneration, rinsing, and backwashing, is 7.3 hours. The last thing we will do is let's calculate the percent of water used for, and I'm going to call it non-productive means. It's water we can't distribute. So for backwashing, we have 12 meters per hour. We'll backwash for 10 minutes, and we need to multiply by the surface area, and that is 14 meters cubed. And this is because it's meters cubed per meter squared per hour. That's that value right there. So that's why we multiply by the surface area. For rinsing, we have 24 bed volumes per hour, or meters cubed per meter cubed per hour, for 25 minutes times the volume, and that equals 63 meters cubed. And for the salt solution, we've already calculated that we needed 9.51 meters cubed. So if we add these volumes together, 14 plus 63 plus 9.51, that's the volume of water that we need for backwashing, rinsing, and to make up the regenerate solution. We're operating at our total flow rate is 0.664 meters cubed per second. We have 16 columns. So we'll divide that by 16, multiply by 3,600 seconds per hour, and the operation service time. This is when we're actually producing water, and that is equal to 0.0936. So roughly 9.6%, or roughly 10% of the water that we produce goes back to the operation of the ion exchange unit. So with the way that we've designed it, you can see why we want to if we can minimize our backwashing, we can minimize our rinse time, we can minimize how much water that we're using for these non-productive uses. So if you need 20 mgd, as we do here, you actually have to design for an increased flow rate to account for the fact that almost 10% of your treated water is being used for the operation. Any questions? So that's the end of this problem. This actually ends ion exchange.